Okay, so we continue. We will start discussing cohomology theory, the LEUNG theory. So let me recall some of the points and some other new perspective. So we start with a manifold M. And we associate is the LEUNG complex. So this is it's okay. Element here. So element could look like F, for example. Okay, and this has two structures. One is the differentiations. So the differentiate, you just differentiate all possible way. So this is df, dx1, dx1, dx1. So when you send d plus df, dx2, dx2, dx1. Okay? But if you are making it skew symmetric, that means dx2, dx1 is the same as dx1, dx2 with a minus, then this one will be 0. And the purpose of making it skew symmetric is what we do here, is to make sure that d squared is 0. And when I say d is mapping this to itself, in fact, you see it's increasing the degree 1 form to a degree 2 form. So this one, sometimes we label it like this, just indicating that you're sending from k to k plus 1. And it also has an algebra structure, this space. Okay, so the algebra structure is a phi eta is commutative up to a plus minus 1, depending on how many times you have to switch this skew symmetric factor. Okay, so there's some sign here. It's a plus minus 1 up to the degree of phi. And then these two structures are related because this is just a differentiation. I mean, everything is just differentiations. So this is our degree of phi. Okay, just a usual differentiation. So this structure giving you that this is a differential graded algebra. Okay, so it's called DGA, and in this case, this is also commutative. This product is commutative, so it's commutative DGA. And forget the algebra structure. The d squared equal to 0 gives you a cohomology because d squared is 0. Okay, and the wedge product still survives here because of this product rule here. Okay, and still commutative, means graded commutative. So this is a graded commutative ring. Because whenever I say commutative, because there's a grading, it's always graded commutative. Everything is graded. Okay. So it's a graded commutative ring. Okay. So let's look at an example. If you look at S2, sometimes people write CP1, it doesn't really matter. Okay. So let's think about it as the unit sphere in R3. This is one here. So let's say you realize that S2 is a unit sphere in R3. Let's say. Okay. Then the cohomology look like this. homology K for S2 when K is 1, this is R. K is 0. Because those are just constant functions. It's always the case when the space is connected. When K is 1, that is 0. When K is 2, that is 1. So we mentioned that because it's a compare-oriented manifold and the top degree and this one are due to each other by point graduality. And to be explicit, in fact, that is generated by a particular two-form. Okay. There are many ways of writing the two-form. So sometimes we call it Fubini student form. Yeah. It's a harmonic form. If you are, when we talk about hot theory, harmonic form will present in the cohomology class. And another way of thinking about it is because this space has a SO3 actions. Okay. And that's if you fix the two-form value at one point and then you just rotate by SO3, that's kind of the way that you get it, SO3 invariant closed form. Okay. To be very explicit, if you look at this one, the volume form on R3 is dx, dy, dz, where x, y, z are the coordinate here. Okay. And you will stick to this sphere, of course, it's 0 because this is 2 dimensions. You can not support a free form. But if you look at 2 of them, okay, so let's say dx, dy, okay, but you better also choose dy, dz, and then dz, dx. Then I think you have to be, I could be wrong here. It could be divided by z, and then x, and then y. So, check. It's an exercise. Okay. You basically write down a canonical form to be invariant of the torus action. So something of this type, yeah. So sometimes you can change this one. Oh, one more thing. Yeah, let's say that. So you get a. So in this case, this is the one. So this, and also, this is generated by the constant function here. And then you clearly see what the ring is as a ring. So this is generated by 1 and this element, but the element square is 0. Okay, so this one is isomorphic to, maybe you can write this as T. Some generator will be just this. I mean, just abstractly, I'm writing this as a ring over T squared equal to 0. Okay, so omega squared is 0. Okay, and let's say we are doing a complex coefficient. I mean, we say in real first, okay. One interesting thing is that usually what we do with a ring, commutative ring, in this case, this is honestly commutative because odd degree is 0. It's not greater commutative. There's no odd degree. So honest commutative. And then you can associate with space for the spectrum of the ring. In this case, the space is just t squared equal to 0. So let's look at this is the t coordinate axis. This is t equal to 0. So this is like this point get double. Because t equal to 0 is just this point, but this is this single origin with multiplicity 2. Okay? It's 1 point with multiplicity 2. And Okay. The questions is in general. I always tell you this. What does this spectrum mean? Okay. What does this? What's the geometry meaning? What does this mean? Okay. So let me just quickly recall you this notion about a relation between a space and the ring. So just recall digressions. That if you start with a space, if it is a topological space or algebraic variety, complex manifold, just in general, a space with some notions, okay, of topology, okay, then you can associate to it all its functions. Functions on M. Okay. So if it is a topological space, you could look at continuous functions. If you are a complex manifold, you look at holomorphic function, and then they are dictated by. You can consider some topology to declare what continuous function would mean. Okay. So let's pretend at the moment that's topological manifold. So just a continuous function in this case, and this clearly, you can multiply functions. The reason is, let's say this is a complex value function. So element here is f from M to C. Okay. So the multiplication is just occur in C. Okay. That's why this is always commutative. C is commutative. So this is always a commutative ring. So you are turning geometry question to algebra questions. Algebraic questions. And from the algebra, you can recover that one. So, and that is the spectrum of that. Okay. And the reason is spectrum of the ring. Let's just call the ring R. And the reason is how do you recover the point here? Okay. If you are given a point here, you should associate some particular class of function. What class of function? Well, pick a point in here. Then you can look at all the functions on M which vanish at that point. There's nothing else you can do because there's nothing else you can do basically. This is very big because this is all the function with only one constraint. This is as big as ideal it can be. So this is a maximum ideal. This is a maximum ideal in R. Okay. So the space M can be recovered as the set of all maximum ideal. And this is basically the spectrum, some kind of maximum spectrum. So the spectrum refers to, you look at all prime ideal. So what is the difference between prime ideal and maximum ideal? And if you have a space ring of function, the maximum ideal is just points. And the prime ideal are functions which may not be as big. Well, let's say they vanish on some subspace. Okay, and that is those functions vanish on some subspace will produce you a prime ideal, irreducible subspace, and the point is, yeah, if you are topological, that's not, you don't really care about all those subspace. That's just too many. But if you are in algebraic setting, you only look at algebraic subspace, so those prime ideals really carry a lot of information, okay, in the algebraic setting. So we're not be very careful about that. So basically, we think this type of strategy works for any like a smooth function, topological functions, and algebraic function. In the case of topological continuous function, that's what the Neumann theorem that says to that tell you that the topological manifold control give you the ring of function, which the algebra is called will be a star structure called C-star algebra, and you can recover the space at space of all maximum ideal. But the main argument in that theorem is not just M as a point set. The topology of M is also completely controlled by the C-star algebra structure. Okay, and that is this duality phenomenon. You can study geometry via algebraic method and vice versa. Okay. So come back to these questions. The question is, while you have a ring, commutative ring, starting from a space, but you have another commutative ring. This is a much more finite dimensional because if M is like a finite topology, let's say compact, okay? So this is a finite dimension ring as a vector space, is a finite dimensional. So finite dimensional ring, you essentially have only a few points. But think about that, if you have more points, then of course you get a much bigger space. Or just like in this example, this is just a 1 point with multiplicity 2. So in general, it's just very few points, okay? So, yeah. So let's see what that means, okay? So that's this question. So continue to that. If you start with a function m, and let's say you associate all its function, let's say it's smooth continuous function or smooth function. Okay, let's just pretend smooth function. We are not to be very careful here, but we're just illustrating the idea to give you an intuitive reason of what you're thinking about here. Okay, so you go from a space to an algebra, ring commutative algebra. Okay, now let's say if the space has some symmetry. Can be, let's say you have a Lie group acting on this one. Okay. Then typically the question about symmetry in both in mathematics and physics is the standard thing you want to do is you make the system easier because you want to take away the symmetry. They become a smaller system, and then that helps you to understand the original system. So the same philosophy here. Then you will try to understand how about the quotient space. Of course, quotient may not be smooth, okay, but let's ignore those issues. Certain those are important, but not at this moment. So how about the functions on the quotient? Okay. The function on the quotient, meaning the function on M, which are invariant under G actions. Right? So these are function on M, which are invariant under G actions. So the G invariant function. That would be the function on the bottom. Okay? And another way of saying it, let me just illustrate the idea when the group is S1, but you don't have to, but just for simplicity. So you have a space. Each point, the group will act on it, and then that will generate vector field V. Okay, so this is the group actions. So each point, you start to move it, and then there's an infinitesimal action that will become a vector field. Okay, so V is the infinitesimal actions. This linearization of the group actions. So that's, in the S1 case, that's only one. Okay, so this is a vector field. And then in this case, you want things to be invariant under the group action. That means invariant under V. Let's say the group is connected. Let's say S1. Okay, so in this case, this is just all the functions which are in the kernel of V. Well, the point is what does the vector field do? Well, the vector field, in a way, is the same as something acting on the functions satisfying the product rule. Okay? In fact, abstract manifold, this is how we define what is a vector field. Because once you have a vector field, then you know how to differentiate functions along those directions, and they satisfy this property. Abstractly, you can just reverse the process. I mean, this is definition of vector field. Okay. All right? And then then when I look at this, or if you can look at this like, you can think about it as a kernel of the Lie derivative. Because on function, the Lie derivative is the same as the vector field acting on function. Okay? All right, so that's the first thing. Let's take a look at the local case. What is the function? Well, let's say M is just let's say this is just some our n. This is in our situations locally. Look like that. Then all the functions. Well, you can look at those which are algebraic function, meaning polynomial. So in this case, it's much easier. So this is a vector space. That's just called a vector space V. So let's say M is just a vector V. It's vector space. Because in that case, then we can say what a polynomial is. Okay? It's a vector space, a polynomial, and that is just. So this is V star will be linear functions, and all polynomial is a symmetric algebra of V star. It's all polynomial. And because we are looking at complex value functions later, don't have to be, let's say real value too. Okay, so this is all the algebraic function, and this kind of some kind of completion here, like convergent power series. So sometimes people write this. For us, we don't. This is not the essential. I mean, we're just illustrating the main point here, and essentially just some kind of a limiting process of having polynomial, whether you want to be convergent or formal power series and so on. So this will be convergent power series. That's it. Okay. Then in this case, then the spectrum in this case will recover this space. That's what we said earlier. So as I mentioned before, what if all you really need is commutativity? Well, how about if this is skew commutativity? Anyway, we are thinking about things which are greater commutative. So for example, if you use this one, okay? So you can still commutative graded. So you can still talk about the maximum ideal. You can still talk about the spectrum of this one. But notice that it's a kind of different. First of all, it's not the usual manifold, because manifold functions are really commutative, not greater commutative. Okay, but in a way, we can just look at the set of our maximum ideal of that. Okay, and this one, you should think about this is really a one point which is kind of thickened or with high multiplicity. The reason is that the huge difference here, this is a finite dimensional vector space. What's the V is finite dimensional, the exterior algebra, the dimensions is of this is n factorial when V is of dimension n. Okay, so it's finite dimensional. That's the only thing I care at this moment. So finite dimensional vector space, you can never really have a big space, because once you move out, there's so many points. Okay? This cannot support a finite dimension space. So this will only essentially just one point. You try to move out to some order n, but you cannot really move out bigger. You can think about it's a point with n different directions. You try to move out, but you cannot honestly move it out. Okay. So, all right. So this is if you look at the tangent. So we are going to write this as a function. We can think of function of this one. Let's say shifted. Shifted, maybe why is this? Shifted by 1 here. This as a 1 is just referring to when you look at the function on that is xy to the power, xy equal to yx up to the power minus 1 to the power 1. Okay, so this is just referring to that this is this odd thing that makes it anti-commute. Okay, there's a notation at this moment you can think about that. Then if you look at both together, meaning that if you're looking at the manifold, that is the first part, and then function on the tangent bundle but shifted. So we're just writing this as this one. Now we also look at the other direction, which is the same. This is function on V, this is function on V, but you want to be skew commutative. So it's meaning also the same direction, so it's tangent direction, but shifted. So you look at this case. And so therefore the function on this, well, two parts. One is this, one is that. Okay? Yeah. And this is just function on M. I mean, you can do it globally now because there's this locus. But this direction is only infinitesimal. So you should think about this manifold look like this is M. And then if you, instead of the tangent bundle, you can't really do the whole tangent bundle. You try to, because it's skew symmetric direction, you try to move up one a little bit. So it's really not a big space. It's really kind of a M with every point with multiplicity N or something. Okay? Like that. Okay. So this is this space. Okay. Then you look at all its functions. What is all the function? Well, you have function on the M part, x1 up to xn and so on. And then you have the exterior algebra of the spring, which is also labeled by the same thing, except but now this is the skew symmetric instead of polynomial, and that is how we write as this, and so on. Okay, so all the functions on here is what we call a differential form on M. Well, what we write is this, right? You have function on the M direction, and then the other direction is this exterior algebra of that. Okay, so this part. So this is what we call differential form on M. Okay. But now notice that there's a very natural vector field on this space because this direction and that direction is the same direction. Because this is a tangent direction, that is also the tangent direction. Okay, so you can look at the diagonal directions. Okay, if it's first order, you have that. I mean, of course, this one cannot integrate it out, but first order, you have a vector field. It's called a supersymmetric vector field. So you just, as a vector field, you just write this right there. Okay, you just call this. So call this Q, let's say a supersymmetry. So it's some vector field on this space, okay? Because of this tautological constructions. Okay? There exists a canonical vector field okay, on this. Remember what I just said. What is a vector field? Well, you can characterize the vector field to be something acting on the function satisfy the product rule. Okay? And this vector field is exactly this. The Dirac differential is a action on here. It satisfies the product rule. Okay? If you think about that, that is this tautological vector field. Okay? The vector field is kind of switching. I mean, as we mentioned earlier, the vector field is mapping from here to here, because you differentiate the function. You make the polynomial of degree k to be degree k minus 1 and switch one of those to dx. Okay? And so the vector field is just the map induced by the identity map. And then you induce to here, and that's the d here. Okay? Yes, that's how we do the Dirac differential. Okay, so that is the vector field. It's all tautological, right? Okay. So once you have the vector field, you want to quotient out the vector field. You want to take away the symmetry. Okay. So that's what we do here. What do you do? Well, we want to take away the symmetry, and that means that you look at all the functions in the kernel of the vector field. Okay? Previously, you only go for vector field to itself, but now D has a property. You can get D squared becomes 0. Okay? So therefore, you should think about that. If you want to look at the functions on this space, quotienting out the symmetry, that should be looking at this one, but you restrict to the kernel of the vector field. Well, previously, the space of functions is just degree 0 thing. You don't have other degree. Okay, but now you have the greater thing. So the map is changing the degree, and d squared is 0 because the fermionic part, so-called this exterior part has a degree. Yeah. So therefore, you should really looking at, instead of just the kernel, it should be, the right thing to look at is because you have shifting degree, should be kernel over image. So the space of, so the cohomology, usually as a commutative ring or greater commutative ring, is just a function on our natural space quotienting out the symmetry. So therefore, the spectrum of that, whatever that is what we should think about it as this supersymmetric space quotienting out the supersymmetry. Okay, that will be just one point basically with some multiplicity going on. This is a finite dimensional space. Okay. And so in particular, the error characteristic is just counting the multiplicity of this space. It's alternating some of the dimension. If the space of function has dimension k, that means you only have k points. Right. So the error characteristic is in some way you are thinking about. It's just really trying to count the right way of thinking about. This is only one point with some multiplicity. This is just the further structure, which are in the ring structure. But this is just referring to the multiplicity. Okay, so that is otherwise you will think, okay, you have a ring. Why you have a ring? Why you look at a characteristic? And this all tautologically come from M. Okay. Okay, so come back to our discussion of the round theory. In this case, we study with any manifold here. Okay, and then we associate to this at the moment, we are not using the wedge product, as you will see later why we're not using the wedge product. Okay. So at this moment, just this one, and the point is d squared equal to 0, and so therefore you can get a cohomology of M. Okay, kernel image as usual. Okay. Let's recall some of the property that we discussed earlier. The first property is this is all we care. Okay, so how flexible that can be. Okay, first possibility is you can replace this one by a section of a bundle, and then if you're a section of a bundle, you choose a connection, and then you need this property to hold true. Okay, then you can still do the same thing here. That's just remembering you have a flat connection here. Okay, so because our connections will give you this one will send to omega m e, just like usual d. You just differentiate section along various directions, right? And this such a choice is called connections. So a connection locally is just differentiation up to some lower zero order thing. Okay, so this is because it's differentiating thing. So the first order is always differentiating, but because they're twisting, so there's some zeroth order thing. So it's a tensor thing. Okay? And the square is 0, is what we need. Those are called, because that is what we call the curvature of the connections. And just recall the statement is, we showed you last time, that if you, because I want to claim is that d square is always 0 order. Okay, say again, d is first order. Okay? So d square in general will look like, well, this is a local calculation. We're asking what order this operator is. So d square is d plus a square, and that will be d square plus d compose a plus a compose d by side plus a square. Okay, so d is first order. This is a second order. These two are first order. This is a 0 order. Okay, but the thing is, the second order is obviously 0 because we start with d, which is d squared is 0 on differential form. Now the question is, how about the first order? We still seem to have two first order things, but because of the Lepschat rule, this is the same as d of a multiply. Okay, because this one, you add on something, has two terms. One is d of a, the other of, and the other is a of d something. So that now becomes 0 order, because this is just something times, this is just multiplication of something. So there was the whole argument that this one is always 0 order, which is a dA plus, 1/2 a squared, basically. Okay? And that's what we call curvature. So curvature is just a tensor, it just multiplies something, and that thing is called curvature. Okay? And as we mentioned last time, frequency curvature is just connection is an infinitesimal notion of integrating along some direction. It's a trivialization along some direction. A curvature is to checking if you go around a small loop and then whether that trivialization is trivial or is it some twisting. Okay? In this case, it's a small loop, there's no twisting. Okay? So that is the same as the whole bundle is completely trivial and it's locally. So the only thing that matters is the fundamental group. You go around a non-trivial loop. Okay? So therefore, flat connections up to change of change of gauge, and you can globally on a universal cover just D basically. So this is a space of homomorphism from the fundamental group. I just recorded what I said before. Let's say it's a rank out web bundle, and then up to conjugation by the group G. Let's say conjugation by this. So sometimes people write at G refer to this action is a conjugation action. Another thing of thinking is this one is the same as you can choose flat bundle is you can choose bundle labeled by transition functions. Flat is the one that the transition function is constant locally. It's the same argument here. There's a constant transition function locally. Okay, and that's so this is what once you have that, and then you can define this one with that one. So this is why I do not want to have a wedge product, because the wedge product of form is the same, but when you wedge product, the bundle will go to wedge product of the bundle, okay, or symmetric product. So there's not a ring here. And that's from last time that if you have three of such a bundle, so you have a short excess sequence of a flat bundle. This is a short excess sequence of things we will be doing. So all these are flat. Okay. Then that it induces a long excess sequence in cohomology. Okay, let me not write down. We just everybody know. Write down. It's just a homology k to k plus 1, k plus 1, k plus 1. And you probably have seen this, but this is extremely important points. Maybe I just write it down that in general, given each of these, you may be looking at the differential form of M with S, okay? And so that may be K, and then you have a D connections to K plus 1, S, and so on, D squared is 0. And you have the same thing for E, and same thing for Q, and then you have this map, and so on, okay? So just this in general structure, and this structure will be so important for the later developments of coherent shift and derived functor. Okay? So let me, they all boil down to this, the initial argument is this, just you have 1 complex, 2 complex, 3 complex. Let's say you have, in general, you have 3 different complexes. So 1 complex, 2 complexes. You have a short excess sequence in complexes. The general statement. So it's a short excess sequence in complexes that induce long excess sequence in cohomology. Okay? People study algebraic topology, they all do this calculation. But there's an important argument was this, that if you are doing this k, the degree k here, this is a degree k here, degree k here, and then this short excess sequence gives you this map, and this one, okay, and then D here, and then the D for B, D for C, and so on, go to k plus 1, and then you do the same thing here. Okay, so you want to induce long excess sequence in cohomology, and that is trivial on B to C, C to D, because it's composing. Now the question is, how do you go from D to B, right? So the only argument is you need a map from HK of D to HK plus 1 of B. Right? These are called connecting connecting homomorphism, and the question is, what is this? Okay? So what to do that? You start with a element here, and an element here. Okay, and then do you want to get an element there? Okay, so you start with an element here. Okay, you already know that because it's in kernel of D, so this is 0 here. Okay, but this is surjective here, and so it comes from some element here. I don't care what element here. Okay. And this is a commutative diagram. So this is 0. So this is 0. So this element will map to, this element will map to 0 here. And therefore, it's excess sequence, it maps to some element here. And let's just call that this. And then you just play with this game that this is well-defined, and this is a long excess sequence, and so on. Everything is just sit down and then just check it. There's nothing else. So this is, but in any case, we call this because this is such an important issue that will come in everywhere later. Okay. Okay. So again, short excess sequence on complexes induce long excess sequence in cohomology. Now the point is, once you have long excess sequence, and then all these things are tied to each other, related to each other. If you have two of them and the map between two of them, then you know the third one. Okay, so that's great, because then you can create new thing from, if the other two is known, so you can construct like coherent shift from bundle theory. Okay, you can just create a new theory because of this, basically. All down to that. Okay, so come back to this. Yeah, so, okay, so you get a long exact sequence in cohomology, so that relate all the cohomology theory. But in this setting, what is very important here is because everything is, the transition function is constant. So therefore, all this map has constant rank. Okay? In particular, if these two are bundle, and this one compatible with that, whatever it is, you can define the Q as a bundle. Okay? There's no other choice because this has to be constant rank. Okay? So constant rank is the point here because D of the rank, everything is 0. So therefore, whatever this one, this is constant rank. This is a bundle, the whole point. That means that you are still in the same setting. You're still a flat bundle in the same setting, okay? But not in the double case, the holomorphic case. Okay. So that's one thing. So this is what I said last time, that you can do the same thing here. Okay. Homological element. Yeah. So in this case, M is a complex manifold. The complex manifold, the point is you can decompose D into D plus D bar on the differential form, decompose into P and Q type, DZ and DZ bar type. And D bar square is 0. Okay? So therefore, you can do a same complex here. This one, you can fix it for any P, doesn't really matter because only using one of the operator. Okay? At this moment, you can do D and D bar, doesn't really matter. But once you couple with bundle, you can only do D bar, as you will see why. Okay? But at this point, you can do D cohomology, D bar cohomology, no problem. So this one will go from K to K plus 1. Okay? And D bar square is 0, so you get cohomology. So this is called the double cohomology. PK, so P is fixed. Okay? D bar cohomology, double cohomology. Okay? Now, you can do the same thing for bundle first. Okay? So if you have a bundle, look at this. Yes, with the bundle E. With the bundle E. Okay, so what do you need? Again, the same argument here. You need to make sure that the square is 0. And the same is you need a transition function to be holomorphic. So you need transition functions to be holomorphic. You don't need to be constant. That is a huge advantage. Okay. Yeah. Now, if you do this, you can also see that this one is just the P form. And that the tangent bundle is also holomorphic bundle. So this one, see what is this first of all? This one is the sections of M. And then this one is wedge P of the cotangent tensor wedge K of the cotangent bar. So it's DZ, DZ bar. Tensor E. Okay, E. Okay. Or maybe I'll write the other way. So let's put the K here, P here. Okay. So this is P of DZ, K of DZ bar. Okay. But we're only doing D bar. So that matter is here, right? The D bar thing is about DZ, you get one more DZ bar. You never touch this one. So this is just, you can just put them together as part of the E, basically. It's the same operator, nothing changed. So this one is exactly the same as, you can pretend P is 0. But you just add to this a holomorphic bundle. Okay, same thing. Okay. So this is just same, by the same reason. This is just the same as the usual d-bar cohomology. In this case, we just don't write the p. We just write as k here. The double cohomology, just write one coefficient. Because you just absorb this to the coefficient here. Okay. Before the break, let me just recall that one of the main advantage is this argument, short excess sequence induce long excess sequence. But now the thing is, if you have two of such thing, you have this one and this one, you only require this one to be holomorphic. So rank may not be constant, okay? Not unlike the previous case, rank is constant. So this does not give you constant rank. Okay? So whatever the quotient should be, okay, and that can be, you get everything the same because you can divide cohomology field as usual because you just pretend it looks like that. And this long excess sequence argument tell you that all the cohomology field you need is there, basically. And that this kind of thing locally look like this is called coherent shift. Okay, and then you can put all this, and then you can define cohomology with value in coherent shift. Just again, that's the basic of the argument here. An example of coherent shift is the following. If you have a space complex manifold M, and then if you have this is dimension n, and then you have some submanifold of one less dimension. Let's say this is even all these questions are local questions, right? Whether this is a bundle or shift, or not a bundle, it's a local. Whether the rank is constant or something. So you can essentially think this is Cn basically. So therefore, hypersurface, you can think about this is zero set of a function. Okay? Okay. So locally it's a function. Yeah. So one condition, so it's a hypersurface. Okay. So you can look at this one. When I say this one, people call it structure shift, but in fact you should think about this is just a trivial bundle. Meaning that the bundle trivial and then transit function trivial, just constant holomorphic functions. So the section are holomorphic functions, it's trivial bundle. So this is just a trivial bundle. Why we call structure shift is because of the other language is this is the manifold is controlled by local holomorphic function, which gives you the structure of the complex manifold. And that's why I call it structure shift. Okay, so these are functions. These are the same as the holomorphic functions on M, right, locally. Okay? Constant function, right? Section means holomorphic function locally. Okay? And how about if you look at those functions vanish on Y? So these consist of functions which vanish on Y. Okay? That will be a coherent shift later. But at the moment, the point is if the dimensions, let's say, this one turned out to be a subbundle. This turned out to be a exercise. Or you should think about this, why this is true. This is using the fact that this is of codimension 1. Okay? And the fact is that this one is a line bundle. On Y. This is exactly corresponding to the fact that dimension Y is a codimension 1 and smooth. And that's a very easy argument because everything is a local. Whether checking the thing is constant, it's local. So you can assume M is Cn and Y is just a hyperplane. Okay? So you just check in that case. Okay? So you can just M is C2, Y is C1. That's all you need to compute. And that we know is that one. But this is exactly if and only if. Okay, so when this hypersurface, you can also, then you can see a obvious short excess sequence. Okay? Function on M, quotient and our function vanish on Y, then the quotient should be function on Y. Function on Y vanish on M, of course, is 0. It's 0 function. So this is a short excess sequence. Okay? Wow. Okay. And these two are bundled in this case. This statement is true in general for any submanifold. And this one is a bundle is because it's codimension 1. It's a hypersurface. Okay, that was on here. Okay. This is a bundle on Y, but this is not a bundle on M. Okay, this is a coherent shift. You're only supporting on Y, so this is not a bundle. In fact, if this one is a bundle, because this one is a line bundle, you can talk about is dual bundle, because if you have a vector space, you can look up a dual vector space. Okay? It's not true for coherent shift though, but this is because it's a vector family of finite fixed rank vector space, so you can take a dual vector space. Because it's bundle, you can talk about dual bundle. Now the dual bundle, if you think about this, this is a vector bundle. This particular vector bundle, okay, again the same thing that you can just think about it, and then you can see that already if you think careful. This bundle has a section. Which is S. So as I told you that locally this is a function. But globally, this is a section of some line bundle. Which line bundle is this one? Just think about it, and you just directly write that down. Okay? And then the zero set of that is exactly Y. Okay? This is a theory of divisor that we should write this line bundle. A line bundle with a section whose zero set intersect the zero transversely as Y. So we write this line bundle as Y, Y. Okay, this is where the labeling the zero of the zero set. Okay, referring to the twisting. And so the original OY is OM. This is, you can think of this as a notation at this moment. Okay? So this, again, this short excess sequence always holds true for complex submanifold, but being a line bundle and all this only true for codimension 1 hypersurface. Okay? And this is extremely useful because this enables you to do an induction argument. Because things for vector bundle is easier, line bundle is easier to handle, and then this gives you induction from lower dimensional space to a bigger dimensional space, or vice versa. Okay, so that is one of the key advantage in algebraic geometry that a lot of argument is doing by induction from. Okay, so the advantage here is. Okay, so then you can do dimension induction in dimensions argument because of this type of argument, induction on dimensions for in complex geometry or later also in algebraic geometry. In complex or algebraic geometry. Because relating geometry of the big space versus the geometry of the smaller space. Right? And then you can keep on cutting it, and so on. Okay? So it works both ways. Sometimes the big space is just CPN, and then you just do this and keep on looking on hypersurface CPN, and then intersection of two hypersurface, and so on. Okay? I can also do it the other way around. Sometimes you know things on curve, then you use this argument to understand things on surfaces. But you can see that this, if you go the other way, each time you go one more dimension is very difficult. So those arguments, most of the time go to dimension 2 is extremely powerful, and to dimension 3 is still very useful, but not as powerful as surface theory. An example of this type of argument is the proof of Serre duality by Serre. Of course, it's more than this, but this was an important part of this, the reason that this functorial type argument work in general. Once you know this true for Pn, then you can do all this kind of induction type argument to do it for everything, basically. Okay? And the proof by Hilsebroek on Hilsebroek-Riemann-Roch formula. And that's an amazing piece of work. So, it's a lot more complicated, but one of the key points is, so this is the first example or the second example of the Artier Singer in this one. But in this case, the argument is because you know it's true for CPN with Lie bundle. And then you just have some very ingenious way to produce this is true for all projective variety. Yeah. You need more arguments, certainly. Yeah. So, okay. So let's continue. That we're just comparing the two sides. This is for any manifold, but then the bundle has to be very restricted to a flat bundle. This is more restricted. The manifold has to be complex manifold, but then you have an extremely powerful way of choosing a lot of other bundle to help you study the geometry. And here is things are more direct, and then you can see a lot of nice theorem in algebraic topology. The first one is the Poincare duality. That you need the following things, that the cave cohomology, let's say this is n dimensions, and of M, and then you can wedge product to n minus k, then you get to the top dimensions, and then you can integrate that. Okay. In order to do integration, you need to make sure that you can integrate, you need orientability, and you need integrate to be in finite number, you need companions or some kind of control infinity. So the most typical case that people look at is compact, but you don't have to, but orientability is always needed. Oriented and compact manifold. Like that. Okay. And these are very infinite dimensional things, but the point is once you descend to cohomology, things are finite dimensional. And in this case, the top degree is isomorphic to R. By integration is oriented. That's what the orientability gives you. Okay, and this is a perfect pairing. Perfect pairing meaning that it induces isomorphism from one to the due of another one. We are this pairing. Okay. And if you have a bundle E here, then if you have a bundle E here, then you have a trouble because you cannot, this will become E tensor E. Okay? So the thing better is this is a dual bundle, then you can take the trace. So E tensor E star, take the trace. Okay? That's still a perfect pairing. Okay? So this is E here, this is E star here, and that's this one. And the argument is the same as before, that you can choose a Hodge theory argument later, but at the moment the proof is this is true locally by combining support form. You can couple with a bundle, there's no problem. And then you use this, again, this Mayer rhetoric argument is the same as using this short excess sequence imply long excess sequence argument. I will use that again in a second. So then you know it's true for small set, and then you keep on patching it, and then 5 lemma tell you it's true for any manifold. That was the argument. You cannot do that here because you cannot have partition of unity in complex manifold. Okay? You can do a Hodge theory argument, but the Sayre's proof, so let's say what is the Sayre duality here. In this setting, is the same, is a H, P, K. So that now this is a complex n dimensions. So it's real as a 2n dimensions of M of a holomorphic bundle E. Okay. And then H n minus P n minus K M and bundle E star dual bundle. So here you also at the moment this has to be bundled. I will tell you the coherent shift version later, but at this moment it's a bundle, so you can take the dual bundle. And then you look at the trace of V, and then you go to the top power. The top power is just the usual cohomology. The same you can integrate and then get a function R. Everything is over complex number, so we have to see. And this is a perfect pairing. This whole thing is a perfect pairing. Okay. But again, as I just mentioned, you can just move all this P to the other side. Okay. So you can assume P is 0. Okay. So, but notice that if you assume this P is 0, this P is not 0 though. This P is 0, then this is n. Okay. So it says that this one is the. So this is just the. We should write as the double cohomology of M with coefficient in the holomorphic bundle E. And then this one, as I just mentioned, this is n minus K with M. But you twist by the top exterior and exterior power of the cotangent bundle. Okay, and that bundle is very important. It's as deserves a particular name. It's called the canonical line bundle. Okay, and so you see that it looked like that this Poincare duality and the Sayre duality look exactly the same. And then you may wonder, why? Well, suddenly you have this canonical bundle here. But why? Well, because this unit look at 0 star form. You need also to be n form. So that's why you have to absorb this back. Okay, that's the reason. Okay. Again, you cannot do the partition of unity argument here, but you can do a Hodge theory argument. But however, this kind of functorial derived type argument that I just mentioned a moment ago, well, in more generality, you can do this for shift in general. The analog for that will be the extension group of one shift and another shift. Notice that you should not take the, if this is not a bundle, it's not locally free, you should not take a deal. And then in this case, this one together with this. This is K and minus K. Switch the two. As a perfect pairing. So in general, there's a notion that you cannot take the deal, but then just there's another slot here. Basically, in general, for bundle, you can just switch it to that has a deal B. It's just like homomorphism, right? Homomorphism of E1 tensor E2 is the same as E1 tensor E2 star today, okay? But if it's not bundled, then you have to do this type of argument. And this is a Sayre duality in general that cannot use this type of, you have to use the multifactorial argument as I mentioned earlier. And then here you have this Gauss-Bonnet-Chern formula. It says that the Euler characteristic of this, meaning the alternating sum of the dimensions of the cohomology. This is a rank R bundle. Okay. This is that may be a psi or something. Okay. Then this one is the same as the R times the Euler characteristic of M, and the Gauss-Bonnet formula tells us that R times the, let's say, 2 pi or something, Pfaffian of a Riemannian curvature of M. Okay, so just some characteristic classes in general, Euler class. And the thing is, why only R? Because the bundle has no curvature. Okay, and then otherwise they have this Hilsenberg-Riemann-Roch formula, and that says that this is a holomorphic setting, meaning that you look at the alternating sum of the dimension of that, as I mentioned last time. That is a chain character of the bundle, which is represented by the trace of the E to the I over 2 pi, the curvature of E, times the analog of this. This is some taut form, so in terms of some curvature of M. So this is some taut form. It's analog to this Pfaffian term. Okay. And here, the powerful statement here is this one is easy to compute because it's a topological quantity. But how do you use it? Well, it's not so useful because this is alternating sum, unless there's only one term. Okay, that would be very useful. So you want to say that in some cases, many other terms are all 0. So here's the Cordero vanishing field. That combined with that, that's what we did in the first day of first class about Cordero embedding field. It says that if all the high cohomology of a line bundle, this is when the vector bundle is rank 1, I write L, just a slide bundle, okay. Rank 1 bundle, okay. Rank 1. Okay. Holomorphic line bundle is 0. This meaning only H0. If the rigid curvature of the manifold has the curvature of the line bundle, maybe I'll write as a blue color, is positive. Then this will be very useful because then you don't have H0. You don't have any others. Okay, and this is a whole industry of generalizing this. I mean, this is good if this is true. If it's not true as much, I mean, there are lots of generalization. There's a huge amount of argument. And the original Cordero vanishing argument used a Hodge theory argument, but that algebraic generalization later because it's too important a result. And then really model on this Bachmann argument, which says that the H1, in this case, only the H1 will work of, let's just H1, let's say, okay. Or C will be 0. You can couple with a flat bundle, that's okay. There's no, because you cannot couple with a bundle with curvature positive. It's not defined. That's only defined when the bundle is true flat. So you can put a flat bundle here, not flat bundle. That's no different. There's no curvature that you can use for the bundle. Okay? So you can only have rigid curvature. But again, you only work for H1. Okay? And that works for all the high cohomology. Okay. So yeah. So here's an example. Just to show you an example. Yeah. Just to give some idea. I mean, I've seen all this general discussion, and I mean, very concretely, this one example you can see is on CPN. PN. So this is all the line in CN. Right? This is the space of all line in CN plus 1. Sorry. All the line in CN plus 1. Okay. And there's a bundle. So you look at a hyperplane, let's say C0 equal to 0, or something like that. And that is H. Right? And so sometimes we write as O minus H. These are just all function values on H, as I mentioned. Okay. As a holomorphic bundle, it doesn't really depend on which particular hyperplane. This is just one hyperplane, so we write as O minus 1. Okay. And let's just remind you this. This is a very beautiful construction here because you see what that is. This is just this is n plus 1 dimensional, and you have a map to Pn where the fiber are lie. And what is that? Well, that is really just Cn plus 1 you blow up at the origin. Explicitly. And let's just show you this map first. And so Cn plus 1, like this. So in this case, we are drawing C2. Okay, Cn plus 1. And then you blow up at the origin. Blow up at the origin. Okay? So now, meaning that all the points are the same, except you replace the origin by all its directions. So you're going to replace this by all its directions. So each direction will give you 1 point. Meaning that for each direction, you have a line. And then you just put all this line here. So in this case, you have this. I just put it vertically. So this is the direction. So this is the direction, P1 in this case. Okay? So this line will become this one, and then this particular direction corresponds to P1, which are all the directions. Okay? So when you blow up this point, you separate out all the line, and that becomes a line bundle. And then that's why you project to P1. And over each point here, which is a direction which determines a line, that is the line, which is the line here, which is the direction here. Okay? So therefore, O minus 1 is also called tautological bundle, because this is the line bundle, O minus 1. This is the bundle, which is the line bundle which parameterize all the line C2. And that's why it's tautological. The line over the line is the line itself. Okay, in that sense, it's tautological. And why I write minus 1 is because if you try to draw a holomorphic section, how do you draw a holomorphic section? Well, one way to do it is the following. This is a holomorphic section. Okay, you just write Cn plus 1 as a Cn plus 1 last coordinate. Okay, so write this as a Cn plus a last coordinate. And then one of this will be a section because now it hits every line at a point, non-zero point. Okay? So this one will hit every line as a non-zero point, except it won't hit all those lines on Cn. So therefore, inside here, in this case, that's only one point. This is the x-axis. This is this particular. Okay. So therefore, in this example, it just hit every line at exactly one non-vanishing point, and then that has a simple pole. These two intersect at infinity. Okay. So therefore, these particular sections, I call it T. These particular sections never zero, but it has pole exactly along a hyperplane. We choose one of them. Let's call it H, right? That's how I call it H. Okay? So it has exactly one pole at H. Okay? And that's why I call it -1, because it's counting the pole rather than counting the zero. And that's also consistent with our early observations why we're called O1, because the inverse bundle, the dual bundle, so this bundle has a bundle section T and then a T inverse in the dual bundle now. And that's what I call S here. So T has no zero, so S has no pole. So this one has simple pole along H, S has a simple pole along H, simple zero along H. So this is a section. And then it vanishes at exactly H. And that's why I call this, depending on the section, OH, or H is a degree 1, H is O1. Okay? And for the same convention, OK refer to, we look at O1 tensor itself, K times, and so on. Okay. And then from here, you already see that what are all the holomorphic sections on O1? Right? These are things which are holomorphic section, but it may have zero. Right? O-1 has no holomorphic section, it has a pole. Okay? O1 has a holomorphic section, and this is a holomorphic section. And the section exactly depending on which hyperplane you choose. Okay? So this is, and now of course if you look at S and 2S or 3S, it's the same zero set. It's just scaling. So therefore, if you're thinking about Pn, this is the projective space of all the line in a vector space V. Okay, so V is some vector space of dimension n. Okay, tautologically. Okay, so each, so maybe I should write it this way. So this is abstractly is some Pn-1. So if you look at all the line in P1, then you look at this dual of the tautological bundle. All the holomorphic section is canonically isomorphic to all the linear functions on V. Okay, that's what it said. S is all the linear functions. Okay, and the same reason, basically, this one is that all the homogeneous polynomial of degree k in V. You need to argue that there's no other, but it's not too difficult to argue. So, in particular, and no hyperhomology too. And that you can use quadrilateral vanishing in this case, okay? Because our Pn itself has a Ricci curvature is rather positive. So this one, the dimension is n plus k, choose k. If you only have L0, okay? And what I just argued here is what happens when k is positive. What if k is negative? You just use Z duality to switch back to the positive side. Okay, so this is true for all k. Okay? True for all Pn, true for all k, true for all L. Okay. And in fact, more generally, you can also compute the dimension of this. These are all computed. Sometimes this is a useful information. This is computed by bot. And you can do an exercise. The only one thing you need, besides all the things that I told you, this is a short excess sequence, into long excess sequence, and so on, you need the following short excess sequence to reduce the long excess sequence. Then you can use it, then everything follow. Yeah, you can just do this at home yourself. So let's just call this exercise maybe. And the hint is just this argument. Is you have a sequence that short excess sequence of vector bundle in this case. Okay. Why? Because what is the difference? The difference involves the P full power, exterior power of the tangent bundle, so cotangent bundle. So you better know what happened to the cotangent bundle or equivalent to the tangent bundle. So because of this sequence, whatever you need to know about any power of cotangent bundle, you break it into line bundle. So everything break into line bundle. And then you know what happened to the line bundle. You just need to keep track of what happened on the excess sequence. Okay? And there are lots of vanishing anyway. So therefore the excess sequence degenerates very quickly. And that's why you can compute that. And what is this? These are called the error sequence. This is extremely important form sequence. You can see this is an example. Yeah. How do you, the line bundle we know, but how to determine the tangent bundle of anything? Okay. And the argument is the following. If you look at the space of all R-dimensional subspace inside n-dimensional space, okay, these are called a Grassmannian. These are all R-dimensional linear subspace inside a fixed n-dimensional. It can be real, complex, doesn't really matter. Okay, so you have a n-dimensional subspace. Let's say I draw Cn, but you can do Rn or anything. Okay. And anyway, let's say you pick a subspace here. So this is some subspace here. And then you want to understand what is the tangent space, right? That's the question, right? You want to write the tangent space tautologically, in some way, okay? So take a subspace. What is the tangent space? Well, the tangent space is this. Well, you remove this. You move the tangent. You move the subspace, right? Okay. So how do you move the subspace? Well, you choose any transverse space. Choose any transverse. Yeah. Okay. Complementary dimensional transverse space, and then any element, nearby elements, you can write as a graph of some map. Okay. So in fact, once you choose this, the Grassmannians will contain a big open subset with all the linear map from S to Q, where once you have this map by F, and then you just send it to the graph of F. This. Okay? That is really in fact, you get an open, dense linear subspace here. Okay? Not just the tangent space. The whole, this is in fact the Schubert cycle, okay, the biggest one. So in fact, you have a whole copy of Cn inside. Okay? And so in particular, tangent space is this, with Cn. Okay? So what if you choose another Q? So the tangent space of the Grassmannians, this way of writing in this way, depending on a specific choice of Q, they are all the same. Because all these are vector space, of course, they are equivalent. It's a tautological way, not choose a specific Q. And that is canonically, this is S. Q. Okay, maybe this vector space, I just call it V. Okay. Okay. So just some big vector space called V. And this is V quotient S. Okay? It's an exact sequence that's independent. It's not a specific Q that matters. Okay? So this is tautological. That's why it's equal. It's not isomorphic, it's equal. Okay? Tautologically equal. Okay, that's it. So therefore this one is S tensor V over S, S star, tensor V over S. Right? And what is the S? Well, so you have a space here, okay? And then you have this tangent bundle, that the bundle that you want to understand, but you have a tautological bundle, meaning that over each S you use the S. That is the tautological bundle. Very sorry that I used the S already. Maybe I write it as E or something. E is not a good notation. That's a yes. Okay. So you have a bundle over here. So over each S is the S. And in our earlier case, if this one is a Pn minus 1, let's say Grassmannians 1n. That is the case that we were interested in. This is a Pn minus 1. And this bundle is what I call O minus 1. As this tautological bundle, over the line is the line. So over S is the S. Okay? That's the end of the argument. Because this bundle, in this case, now become O1. Okay, let's see. Then we twist that by this bundle. We tensor this to the other side, S. That is a V over S. Okay, V is the trivial bundle. So V is the trivial bundle of rank n. So this is really the structure shift to the power n, and on n minus 1 is Pn. And then the kernel is S. And this one is S. S, in our case, is what I call O minus 1. It tends O1 or O minus 1. You just take a look and then you go back and get this graph sequence. Yeah. This plus 1. Yeah. There's a tensor back. We got that sequence. Okay. So just give you, at least a very concrete example, you get kind of a taste of how this type of argument works. Okay, so again, what I said in the very beginning is short excess sequence in complexes, right? Give you long excess sequence in cohomology. And the one that we used earlier is we are looking at omega star of m. It could be Debye, Debye, doesn't really matter. Of this is m, okay? And then we use it. This is the one that come from here, right? You're breaking this one up, okay? And now we also, in fact, use this the other time. We're breaking the M, which is called the variatoric sequence. Okay. Alpha sum in this set. So the argument that we used was you break the manifold into many. So this is U alpha, U beta. Then the intersection, U alpha intersect U beta. Let's just, for simplicity, write that U alpha beta. Don't we have to repeat it many times. And then the point was then we will be using this cohomology of individual pieces, maybe alpha 1, alpha 2, alpha p, and so on. And then the whatever thing you restrict to this alpha. So all this kind of data, I mean, there's lots of such data. And then we kind of patching them back together, right? That's my rhetoric argument. And then to recover what we have here. Okay? So all we really need is to have a thing that we understand. And also, in most of the cases, once you do this, if you assume this one is a very local, and so local that you really only have H0, okay? Because there's no, just like Poincare lemma, something. All this cohomology, you really need on a very local pieces, you have things pretty trivial. Because otherwise, every local thing has something that you add up to be infinite dimensional already. So essentially, it's something here, but it cannot be too big, so you can twist to put all this finite thing together is to get some finite dimensional space. Okay, so you need, so let's say that this one has no high cohomology. So really depending on the section of this E, basically. Okay, and then try to put them together. And then the point is that to turn the table around, we just see how much this works. We don't really need that many things. Okay, you only need to have some local thing. Because the whole idea of cohomology, you should not have too many information locally. Otherwise, you get infinite dimensional cohomology. Local things should not be too much, and but they have something that is coherent shift data, and they can patch them together in some way. Okay, so what we need certainly is so you see that everything we will keep on using is this short exact sequence in complex in pi long exact sequence in cohomology type reasoning. Okay. What we really need is this local data is the following. Okay. So you need a space. For this purpose, you don't even need to be a manifold or anything. Okay. And this kind of local data, okay, you need that at the moment called predictive. What we need is you look at a very small open set, or in general, let's say take any open set, okay, and then you have to have something like a section of a bundle or something. Okay, could be holomorphic, smooth, continue, locally constant, doesn't matter. Some functions. What we need is the following. To put things together, remember, we have to add thing, subtract thing. It better be abelian group, okay? Because then otherwise, you need delta squared to be 0. And then if you're not commuting, then the restriction to restriction will not be 0, okay? So you need that. You need this to be a abelian group or something abelian. Then you can add something, add and subtract. And if you have a subset, because that's what we need, you have something on one chart, another chart. You have to see what are they coincide on the intersection. So you have to a way to restrict to some subset. So you don't just abstract it, just call this restrictions. Just some map, okay? Some map homomorphism of abelian group, but we're thinking about the restrictions to the subset, okay? And satisfy the obvious property. When you restrict and restrict, you can do one restriction one time. It's got obvious compatibility. Okay. So this may not be good enough, but this will be able to run and put things together. Okay. And so if you write M, so such a thing is called pre-shift. It's called pre because clearly this is not the ideal thing that you want yet. Okay, yeah, pre-shift. And then if you write M as a cover, by something. Okay. Then you can do this Maria-Rhetoric type thing to look at on chart, and then you look at the intersection and then put them together and so on. Same argument. Then you can get some abelian group. Depending on, so this is a, let's just call this as a covering. So I don't have to write this whole thing. So this is a, I label the covering by script U with a bar. Okay, so depending on this covering of this picture. Right? And that was just a Maria-Rhetoric, same thing. So that's abstractly doing that, and that you don't, that argument is this. And you get some abelian group. The vector space and this vector space. Yeah. So this is just the minimum amount of thing that you can use to define this. Okay. But of course, it depends on the covering. For example, if this U is just one set, which is just M itself, there's only one open set. Right? There's no restriction or nothing. It's just one thing. So in this case, that this one, this depending on this covering on S, is just degree 0 is just the whole thing on this open set, and non-zero degree is all 0. Because all these other non-zero degree come from how many open sets you are doing the intersection of those. There's nothing, there's only one. Okay, so the whole point about this is that you want to break it into smaller and smaller pieces. Because think about if this is holomorphic functions, and if you look at global holomorphic function, you only have constant. That's not what you want. You want to see the higher cohomology. And that really depending on local holomorphic function cannot extend globally. But then you have, that's why those information is captured in cohomology field. All right? So first of all, you want to choose a very small open set. Okay? So in any case, if you do not want to depending on the covering, you just divide by the direct limit of all the covering. You just do the refinement of covering. You know, just, if you, because of this property, you can do refinement, you can deduce a map on cohomology. Just look at the limited space. Okay. So for example, if you, the original Maria-Rhetoric argument was saying that if you do this, if M is a manifold, and the shift, and this one is just a constant function. So maybe I write it this way, in the sense that delta meaning that the discrete topology, meaning that continuous function means constant function. Okay, continuous function. So you look at locally constant function. So in this case, the Maria-Rhetoric statement is exactly saying this is the usual Durand cohomology that we have. So this is just rephrasing what's the Maria-Rhetoric argument. You break the cohomology into smaller pieces, and then you put it back. Okay. So. But if you do a similar thing for smooth topology, that is very different though. That one is 0 if this degree is not 0. If degree is 0, this is just all the smooth function on M. So that is the original idea that all the cohomology is measuring how a local function extends globally. So if it's constant function, local function, when they extend, there's all this topological data. But if it's smooth function, any smooth function extend, well, any smooth function on M, let's say locally on U, may not extend, because if it's defined on 0, 1, it may go to infinity. It may not extend. But if you make it slightly smaller, then it extends. Okay? And such a property is such shift is called a fine shift. So in algebraically, then you cannot say cut it smaller. I mean, that's a flat shift. But in this case, essentially, say that everything extends. Well, because essentially we're looking at things smaller and smaller anyway. So if you are allowing slightly smaller can extend, that's really no cohomology at all. Okay, all the sequence split, and then you go back to the no higher cohomology. You just have H0. Okay. And similarly, because the same thing, I just put it here. If you look at this one, but look at holomorphic function, well, holomorphic function map to C. Okay. So meaning that if you look at it, so M is now a complex manifold to make sense of what holomorphic function is. Okay. So again, the definition is on each open set, you just look at holomorphic function as the S. Okay. And again, the same type, because it's just a Mario-rhetoric type argument, making this manifold to be covered by open set and so on. And this is what we define as the Wolf cohomology. The same for bundle, holomorphic bundle is the same. Yeah. All this, I mean, you can put a flat bundle here, and a smooth bundle. But smooth bundle, no cohomology. All right. So what I'm going to do? Let's just look at this again. Or this. So the thing is, there are lots of functoriality property. We just want to make use of functoriality to see how far things can go. Okay, and you can see all things come from all this exact sequence and so on. Okay, and so for example, if you have M and then S, right? Some shift. Oh, I haven't recall what it. Why do I call P shift and why I think what are the shifts which are better? Okay, shift is the following: is a pre-shift, and things really controlled by local property. Okay, really behave locally. So which is like holomorphic bundle. You want things which essentially all come from like local data. Just like because of like bundle theory, everything essentially controlled by local data. And the definition is plus another thing. Okay. And if you write some open set as some union of some V alpha, you don't have to be M. Maybe some, and whenever you inside M, you have an open set, which is a bunch of the V1, V2, V3, and so on, and this is okay. Take any open set. If you break it down, and then you can build the whole thing back. I mean, everything is controlled by the smaller pieces. That's what it means. Okay. So the first property is if you have something defined on the whole thing, and then it's 0 on each part, then it's 0. Okay. So if it's 0 on each open set, smaller set, then it's 0. That means that when you want to see what happened on a big open set, it's controlled completely on what happened on the small open set. Right? It shows those which are compatible. And in fact, exactly that if you have each of them are compatible, so each of the VI has one of these SI, and then they are compatible, meaning that the intercept on Vij are the same for all Ij, then you can piece them together. Okay, then there exists S and SU such that Si is S, the restriction of S to Vi. Okay, you just say that it's determined by local data and also determined by determinate and also determined by it. Okay, if zero locally, it's zero globally. If you locally have something which is compatible, then it's come from global. Okay, so things are essentially eventually local data. That's what I call a shift. Yeah. And basically, all we look at all the geometry things are shift because things are really starting from local completely controlled global. So pre-shift was just the minimum thing that you can use to define cohomology. But only shift thing has better property. Okay. Down. So the section here. It's not a chapter, it's a section. Derived functor. Okay, so again, the main point is the thing that I just want to erase. So short excess sequence in complex imply long excess sequence is this type of idea in cohomology, right? That was the homological algebra lemma that I just said. Right? And then you can put many of such together that give you the following. Then if you have this, there's a lemma, a proposition, if you like. Okay. So you have so all these are shift. Okay, excess sequence in these are excess sequence in shift, excess sequence in shift. Okay. And then you have S. A1, A2, keep on doing it, such that this one has no cohomology, high cohomology, such that all of this has no high cohomology. Okay? So such a thing are called acyclic resolution. No high cohomology is acyclic, and such a thing is called a resolution of S of the shift. Okay. So this only have H0. And then you can break this one into many short excess sequence. And then you can use short excess sequence in complex determinant. Long excess sequence in cohomology, but the cohomology is pretty trivial. And therefore, this check cohomology is H0. H0 is always this one. Okay. And let's say K. This is on the K level, and this is the kernel of an image. Okay, it's general statement, any shift. Okay, and in particular, it looks so familiar because this is what we do in the RAM cohomology. But you can do it very generally. So example is to do this shift. It's just a locally constant function. I mean constant function locally, right? Constant function shift or locally constant function shift on M. Okay. Then this one is a cyclic resolution. Why? Because what is this? Well, the first term is omega 0 M. This is the same as all function on M, which is the same as R, but with smooth topology. Right? This is smooth functions. Continuous constant function, of course, is smooth functions where D is 0. Okay? And similarly. So This is so-called this fine shift because you can do this partition of unity, any small function. If you look at smaller open set, they can always extend and so on. There's no higher cohomology. And all the other things, because whenever things are smooth, and the partition of unity argument tell you is that you can extend things. No higher cohomology. And so that's just that lemma is a triple lemma. That's that. Then the check cohomology of M with this discrete topology is the de Rham cohomology. That's how we define that. Because a global section is just exactly this. Right? Maybe this is not, this should be, you should write as a shift, meaning that these are section of the K power of the cotangent bundle, but we refer to the smooth topology. Okay, just smooth sections. Okay, and you get a D. And the global section is a differential form. Okay. So this is this lemma, and then what we had earlier is this is the same as the de Rham cohomology of M. Well, this is how we define it anyway. Okay. It's just going around a circle, the same thing. Okay. So this argument of getting a cyclic shift, you see that this acyclic resolution is very useful in this example. So this one has this property. Let's say at K here. The thing is, as long as you use smooth topology, smooth section of bundle, you can always cut it a little bit and extend. Right? And this has a partition of unity argument. This one, partitions of unity argument, will tell you there's no higher cohomology. This shift itself, sorry. This shift has no higher. This one itself has no. This no high check cohomology. Okay? Because everything extends if you're allowed to make it slightly smaller. Okay? And abstractly, you can just write down what partition of unity argument go, and those shifts are called fine shift. Definition of fine shift is so that partition of unity argument, well, basically. Okay. So you can define yourself. And but if you are not on manifold, if you are doing in algebraic geometry or more general setting, you can't do this thing. I mean, because it's a not smooth function. You need something like this. Okay? You only need a cyclic, though. How do you find those acyclic things? Okay? And you get the strongest one. That will imply that. That is just say that you don't have to restrict to smaller ones, just extend it, okay? Well, then smooth function does not, okay? So this is a smooth function does not satisfy this. So this is a definition, is for all S that extend. For all S in U that exists, you can always extend. Everything extends. Maybe the other way. This is S0. So S0 restrict to U is S. Okay? You don't even have to restrict to a smaller set. So of course, then you need, if you are doing this kind of constant function, smooth function is not good enough. It does not satisfy this, right? But fine shift is already enough. But that argument you need to be shrink a little bit to do. But this is a more algebraic argument. You don't even need the topology of a manifold or anything. Okay? And so when you can do that, okay? No topology related, okay? And what we really usually need is an injective object. That is enough. A reference of that is chapter 3 of Hartshorne. Yeah. Okay. So, so need So most algebraically, and you can achieve this, so it's only need so-called injective resolution. Instead of, those will be good enough to get acyclic resolutions, injective resolutions. The reason is the following. Abelian group and all this has enough injective resolutions. Okay, so what is that? Let me just say that. Then at the end, you just turn the table around. You just abstractly define cohomology theory. If you have all this property, then you don't need a manifold or you don't need anything. Okay. So that's just what we call. So R is a commutative ring with identity, okay? And a R module, the thing that we were thinking is, for example, we may be looking at local version, maybe or the function on a complex manifold, right? And it's a complex manifold. This is not a ring, but it's a sheaf of commutative ring. Okay, you can do it very generally, and then you can ask whether you have enough injective. Okay. Okay, so what is an injective? Injective will give you a sacred resolution to define cohomology already. Okay. And one more thing, let me just tell you, because this cohomology is defined independent of the choice of sacred resolution. So you should imagine that if you try to define this, you don't know the original definition. But you just define by, if you have a acyclic or injective resolution, you just define this way. This should be independent of the choice, right? Because this is independent of the choice in this case. And the same argument will tell you that this type of algebraic argument will tell you that you can, whenever you have something, so you have an injective resolution that will be acyclic, then it's independent of that choice. Okay, so you can define that. Okay, so what is injective first of all? A R module is injective if kind of like you have something you can always extend. Okay, so if you have a excess sequence of R module, and then if you have a morphism here, then that exists the extension. So you can already see this is similar favor that you can always extend things, that kind of thing. Okay, that is the definition of injective, and that will kind of break you to those things will eventually give you vanishing of cohomology. And the thing is, in this case, OM module, okay, like coherent shift, that will be OM module. And coherent shift does not have enough injective, if you look at those. That's where you need quasi-coherence, okay? You need quasi-coherent shift. If you look at this type of module, quasi-coherent shift, then you need to use quasi-coherent shift. Because you need to make the thing very, very, very big. So coherent shift is bundle quotient by bundle, which is a finite rank. Clearly, it's not that big. I mean, it's not like differential form of those. You need to allow infinite rank quotient by infinite rank. Okay, so that's why you need to go outside of coherent to define this theory in general. Okay, to have enough injective, there's enough injective, and that's where quasi-coherent is needed, because you need to make the thing very big. Okay. The point is, well, why any of this is true? And they all boil down to the first example, abelian group. Okay, and everything is, using that. Abelian group, you can create enough injective for its module, and then everything just comes from abelian theory, and it's keep on building thing. Okay, and the main point is, for any abelian group A, We'll just for brief. Okay. And then the A module has enough injective. And then you have to look at things which are very big to gain enough injective. That, like if you allow all the smooth differential smooth form and those things. And then this is just a abelian group argument, so in algebra. And then you can use this type to build on everything related to abelian group. And that's why you need quasi-coherent shift there. Okay, so let's say, let me say a few words about what are these examples that give you. Okay, so we have seen some of the examples. We want to see what are the more general examples. So that is will give you. So the idea was the following. If you have this kind of like a category of A module or coherent shift, okay, you look at some object. If you have enough injective, you take an injective resolution. Okay, and then just define the this hypothetical derived functor, and then by taking this one. Okay, so let me show the example. Okay, so if you have a abelian category, everything dependent on abelian. It's important. So abelian category means that the home is abelian group. Home between two objects is abelian group. Okay, and then let's say you have this one, A, to the category of abelian group. That of course is abelian category. So typical example is this is a category of all shift on some manifold. Okay, any type. It can be locally constant shift, smooth shift, holomorphic shift. Take whatever the frequency you want. Okay, and then you just take global sections. That's why we use gamma. Okay, the thing is the derived functor, this kind of data is if you know how to take global sections, you can break it into smaller pieces and then piece them together. Okay, you need enough injective to know that you can do this piecing together, and you get cohomology. Okay, so once you have this one, for example, you go to global sections. So this is just a global section to abelian group. So this is a gamma, is a global sections. Okay. Then you do this. Again, from the same. So this, then you get this. Okay. And provided they have enough injective. Okay. Injective object. So again, the argument is exactly like this. So all these are in the same category A. So you take one object here, because you have enough injective in the abelian category, you take injective resolutions, which will be, we don't care if this is acyclic or not, because at the moment we don't have a definition of high cohomology, but they will be once you define that. But you're thinking that it will be like smooth function extent. Okay, so you just have take any acyclic resolution, and then you define the cohomology like this. Okay, so here's the definition. This is exactly like what I did here. So the construction is choose any for any object here, S in here, okay? Because if enough injective, you get an injective resolution. Let's copy down this one. Okay, and then you just define RK of gamma of S or S. You don't even need a manual for anything. Right? Just define as kernel of delta of an image of delta on the global section, which is defined there. Okay. then you prove that this is well-defined, independent of the cyclic resolution using this definition. If this is acyclic, then it has the property there's no higher cohomology anyway. Okay? Yeah. So well-defined. So and then you prove all this property as expected property, as all the other cohomology we have. All these are just homological thing. I mean, you just because of this example, you see what you expect, and then you just check that. Or because all the argument proving all this are homological algebra argument. You just work in general for this. Okay. So even more generally, you don't need this to be abelian group. You only need to be another abelian category. Okay. So you can replace this by another abelian category, and then just get this. Another abelian category. Okay, let me show you a few examples. And then let's finish that, and then we'll finish chapter 3 of Harshans. Yeah. Example. So the first example is what we had earlier, is this one. Right? So the example, if gamma is this way again, it's a sheaf over a space, then you map to abelian group by global sections. Then RK of gamma of a sheaf on M is just the usual check cohomology. Depending on what level topology. It could be this, could be the round cohomology, could be the bowl cohomology, anything. Okay. And another one. Okay. And you can do other things like extension group of coherent sheaf. I mean, you can find that in Harshad, for example. Okay, so that would be a abelian group. By similar favor, basically, you're just looking at. So all this has a property that if it's 0, that is the global sections. Right. So you see what this is. You want to divide that. You look at that for 0. 0 is just in that case, you have two sheaves. So x0 is all the. So you have two sheaves. Then you can look at the map between them. Okay, and then the derived data is what I called earlier the extension group, which is what used in cellularity. And you don't have to look at global sections. You can look at local sections. Meaning that this is not an abelian group already. This is another sheaf. Okay, so that would be another sheaf on M. Okay, not taking global section, just locally indicated homomorphism, and that would be extension sheaf. So that will again be sheaf of S1, S2. Okay. Another example is a direct image sheaf. So you have a map from M1 to M2. Most of the time you're thinking about this a holomorphic map, but you don't have to. You can do it in smooth topology. I mean, other setting to any of the setting. And then the thing is the original gamma is that you have so gamma is sending sheaf on M1 to sheaf on M2, it's just a push forward. So this one is just a push forward of a sheaf, because you just look at a section of the open set. This becomes defined by section of the pullback of the open set, which is still open. Okay, so that's so let me just write it down. So pull back, and then you have some open set called U2 in M, and then the push forward of a shift. So this will be shift on M2. So you need to evaluate, look at what are the section over U2, which are open set in M2. By definition, is just inverse image of U2 inside M1. This is open set, and then you just look at the shift on that, tautological. Okay, so this is the. So for example, if M2 is a point, okay, and then this is just the global sections, okay, if M2 is a point. So this is a family version of the global section, okay. So then you just look at family version of all this. Instead of a cohomology group, you get a family version of cohomology, and that's what this direct image shift is. So then you get cave direct image shift of that in here, okay, same. So this one, in an algebraic setting, algebraic geometry setting, basically is a family version of cave cohomology of the shift fiberwise, most likely. But I mean, because shift is jumps, the more tricky information. But loosely speaking, that's what it said. Okay. So that is important so you get a family. So Hilscher-Riemann-Roch formula is useful to tell you the alternating sum of the dimension of the cohomology. Let me just say one word here. So when M2 is a point, this is just a usual cave cohomology. Okay? So remember, Hilscher-Riemann-Roch say that if you have a manifold over a point, in this case, this means just a manifold. Okay? And then you have let's say a shift, or let's say a holomorphic bundle, for example, holomorphic bundle. Then the alternating sum of the cohomology, the dimension of the cohomology, should be minus 1 to k. Dimension of the cohomology, sum over k. M is integrate on M1 chain character of the bundle E times the toy class of M1. Now what happens if you have a family? So you should thinking about, well, it don't have to be a fiber bundle. Let's just think about, pretend this is a fiber bundle. This is a very general statement though. Let's pretend this is a fiber bundle. It can even be inclusion in fact. But it's easier to think it's a fiber bundle. Okay, let's say this is a fiber bundle. It's M2 and then M1, and then you have all this fiber. Okay. Maybe I should write this as X, maybe it will be better, sorry. So the fiber look like X. Okay. So I'm kind of thinking this is look like a family version of that. Okay? But again, this is very general, any map in this case. And then you have a bundle here. So therefore the bundle, you think about as a family of bundle over X. Primary choice by M2. Okay? And this is a family of those vector space, right? So you should be thinking about the alternating sum of this thing. Okay, so each of these, for each k, this is a bundle over M2, well, not bundle, coherent shift over M2. But locally, it's a quotient of one bundle over another bundle. So these are alternating sum of vector space family over M2. They can jump various ways. And in fact, that is an element in the K group of the base space. Because you can think about it's a different of vector bundles. Okay, it's a sum and minus. So loosely speaking, it becomes element here. Okay, it's a bundle. And then what is this? Well, now this is the whole. Now E is really over the whole M. 1. So this is over the whole bigger space. But you want to only do it fiber-wise. So you're only looking at the toy class of the relative tangent bundle. So we write in this way, meaning that this is family. This is the thing on M1, but you only look at the vector bundle, which is the quotient of the tangent bundle. So it's a relative tangent bundle. Okay. And this is some kind of cohomology upstairs. Okay? This is a vector bundle. So you take some train character of downstairs to make it into cohomology of downstairs. Okay? But you have to integrate the fiber. So just integrate the fiber. So you can write the fiber-wise integrations, or you can write this as the F, or the push. You write F star refer to integration on fiber in the cohomology. Okay? And that's called the Grothendieck-Riemann-Roch formula. As a family version of that. And again, I only tell you this is a fiber bundle, but this is again for any map basically, not fiber bundle. Okay. Yeah. Okay. So stop here. So.